Hello, good day, whatever part of the world you're watching this from. It could be morning, evening, afternoon. Um, Welcome to the Technical Challenge series. And my purpose, the goal that I want to achieve with this series is to take us through practical, demonstrable, everyday programming steps to solve many of the popular coding challenges that are available on the internet. So, every episode we will pick a popular coding challenge and we will solve it together, within a maximum time box, perhaps an hour. you know and these things will help me share with you, many of you whom are students and aspiring software developers, programmers to be precise, will share with you the mindsets and some of the concrete technical practices and steps that are taken on an everyday basis to build software solutions. So, if you just Google Mars Rover, as in Mars, M for Mango, A for Angular, R for React, and S for synthetic, Mars Rover, you will find um, I mean, an unlimited number of this variations of this problem. So the problem statement is on the screen, just as you can see. Very simple, straightforward. Quite a number of technical recruiters and technical organizations that want to recruit software developers use this problem as a filtering criteria. I have my reservations about the compatibility of the natural temperaments of most programmers with the kind of temperament that is required to succeed in the high pressure that is present in a typical coding interview. I think that there are other ways, there are other more productive ways to establish what they want to establish, but that's another kettle of fish, and that's another issue to tackle on another day. Today, we want to tackle the Mars Rover programming challenge. So without much further ado, let's go. As you can see, I'm using a Mac. I'm going to be using Visual Studio on a Mac. One of the reasons why I like this particular problem is that it's simple, it's straightforward. It's the problem description comes out in typical user language. There's no class described here. It just describes normal, natural language, to use that phrase, to use that term. And you will see when we start to do the technical challenge, the technical implementation, how natural language and words, keywords extracted out of natural language, natural prose like this, becomes the programming constructs that you know and that you've heard about. So classes, structs, enums, properties, blah blah, methods, blah blah blah, and all of those things. I also like it because it is simple and straight to the point. Um, it does not require any. It doesn't require too many dependencies. In other words, in order to finish this problem, in order to solve this problem, you don't need a database, you don't need network access, you don't need dependencies on other layers of or other things, other technical components. So you can just build one or two or three or five or 20 classes, depending on your design, and use that to solve it. So that is that. I will be using Visual Studio. So I'm loading that up now. Visual Studio. New project. .NET Core, of course, this is Visual Studio, so .NET Core. Let's do a console application. Shall we do a console? Shall we do a console? Okay, let's do a console. Yeah, let's do a console. C Sharp, of course. And then let's name it. Did that? Oh, I don't think it got that command. Let's name it Mars Rover. And we will place it somewhere. So I have this funny folder structure that I use coding series, Mars Rover, it's empty, and let's place it in here. Okay, and create a project directly within solution directory. Git for version control, not yet. We will initialize it at a later time. So let's do that and create. And just in case, for those of you that are not familiar with Visual Studio on Mac, that's what it looks like. It's the simplest thing to use. From the day I found it, I now find it difficult to justify getting a Windows box, so, or rather going back to my Windows box, so, well, I mean, things are looking good. Alrighty. So, okay. Okay, so a few things to note. 1 second before I go on. I'm just going to go back to the problem statement now so that we can look at it together. Okay, and just before I do that, let me quickly say that, as you can see here from the last project that I ran, I have the unit test panel open. Otherwise, I would just go to View, Test. But what I wanted to say here is that the very first thing I would do typically when I want to build applications nowadays is to create a test class. So the background to that is I have been sold over by the TDD bug. I have bought into it, and that's just what it is. So the era of writing code for the sake of writing code for me is over. So I only write code that passes a previously failing test, and that test itself must have been derived from a requirement in the problem statement. So you will see how that works now, and without much further ado, let's do that. Let's go there. When we come back, we'll create our test project. So the problem statement says a squad of robotic rovers are to be landed by NASA on a plateau on Mars. This plateau, which is curiously rectangular, must be navigated by the rovers so that their onboard cameras can get a complete view of the surrounding terrain to send back to Earth. A rover's position. Okay, so let's jot down a few things as we move along. Okay, we could do the popular Mac split screen here. Visual Studio. Ooh, it doesn't want to share. Visual Studio does not want to share. Visual Studio does not want to share. All right. Okay, so okay. I'm gonna have to do them side by side then. Okay, so a squad of robotic rovers are to be landed by NASA on a plateau on Mars. This plateau, which is curiously rectangular, must be navigated by the rovers so that their onboard cameras can get a complete view of surrounding terrain to send back to Earth. A rover's position, so I already have a notion of something called a rover. From the first paragraph, I have a notion of something called, so I like to do this, okay? In the interviews that I've conducted in the past for potential, recruits into my teams, in the past teams that I've led, I look out for a certain trait when I ask potential candidates for solutions to technical problems. I especially am more interested in the candidates who display a problem-solving acumen over the candidates who display a pure programming acumen. So for me, it's very important for a programmer to start any programming task, first of all, by breaking down the problem that programming task is trying to solve. So something as simple as just writing out a number of comment lines that say, step 1, loop Step 1, declare variables. Step 2, loop, declare array. Step 3, loop through array. If I equals 1, exit array, blah, 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 and so on and so forth, that kind of stuff. So you see a lot of comments here, and that's that's the concept I'm trying to explain here. So from this first paragraph, from this first paragraph, there is a notion of a mission, a NASA mission, okay? So there's something called a mission or a message, whatever you want to call that. So let's call that a mission object, okay? Its parameters, its attributes and behaviors we will take in a moment as we learn more about the project. A rover's second paragraph, a rover's position and location is represented by a combination of X and Y coordinates and a letter representing one of the 4 cardinal compass points. What are the 4 cardinal? First of all, position, location. So those are attributes. And attributes of what? A rover. So that's another object. Rover, position and location represented by X, Y. Okay. And a letter representing one of the 4 cardinal points. So we could say X, Y, and Z. Okay. Where Z is a member of, or Z is in this set of values. N for north, E for west, E for east, W for west, and S for south. Alrighty. Representing 4 cardinal compass points. The plateau is divided up into a grid to simplify navigation. So the plateau is divided up into a grid. What is a plateau? What is a plateau? The plateau is divided up into a grid. So there's a concept of a plateau upon which the rover lands. In similar challenges, this, for instance, the tower defense game, this might be a map object, but just over here, it's called a plateau, so let's call it a plateau. Maybe later on we can come back and refactor and rename it to a map, but for now it's called a plateau. The plateau is divided up into a grid to simplify navigation. Okay, an example position might be 0, 0, N, which means the rover is in the bottom left corner and facing north. So it appears that the plateau also has X and Y coordinates. Okay, the plateau is divided into a grid to simplify navigation. So grid of positions following the format X, Y, Z. Okay, 0, 0, N, X, Y, Z, which means the rover is in the bottom left corner and facing north. So if you have 0, 0, N, the implication is that 0, 0, N means X equals 0, Y equals 0, and Z equals N. Alrighty. So requirements are getting clear. We're extracting requirements out of natural language. In order to control a rover, NASA sends a simple string of letters. In order to control a rover, NASA sends a simple string of letters. Can we call that a command? That's a command. NASA, back on Earth, is sending a simple string of letters to the rover on Mars. Okay, interplanetary command. So let's call that a command or a message. Maybe a message, just just for semantic purposes. Message. So the message is a simple string of characters. String. Let's not complicate things. Let's just leave it like that. We'll come back and flesh it up. The possible letters are L, R, and M. Okay, where it must be okay, let's do this. Let's say A, B, A, where A is in L, M, did I say L? Did I see LRM? LRM, okay? LR and M. And where LR and M represents LR and M represents L and R makes the rover spin 90 degrees left or right respectively without moving from its current spot, and M means move forward one green point. So if you interpret that, essentially what they're saying is L equals left, R equals right, and M equals, what can we call it? Move. L is left, rotate left actually, spin left, okay, according to their terminology. So let's call this spin left, spin right, and then M is move forward one green point. Move forward, okay? Let's see, is there anything more to extract? Assume that the square directly north from xy is xy plus 1. Okay, I guess what that means is the only difference between xy and xy plus 1 is that y was incremented by 1. And when you want to move north directly, the grid position directly north of the current grid position must be 1 increment higher on the y plane, on the, what do you call that now, on the y axis, so that's pretty straightforward. That just confirms assumptions that we're using a regular Cartesian plane. The first line of input is the upper right coordinates of the plateau. Now where's the input? This is the input over here. Okay, this is the input over here at the bottom of the screen. The first line of input is the upper right coordinates of the plateau, 5, 5. So I guess all of this, line 1, 2, 3, 4, 5 are the inputs. So the input is a 5-line input. Very important. Input equals 5 lines. Okay. And obviously output equals 1, 2 lines. Okay. We'll come back to that. The first line of input is the upper right coordinates of the plateau. The lower left coordinates are assumed to be 0, 0. Okay. The first line of input is the upper right coordinates of the plateau. Ooh. Technically speaking, they just gave us the size of the plateau. So if the lower left coordinates are 0, 0 and the upper right is 5, 5 from this example, that means this grid is 6 squares by long. Is a square of 6 sides, of 6 squares, 6 units long and wide. So what that means, according to our system, according to our solution, is that our map object has to have a size. So if we go back to the plateau grid of positions where we'd also need to add something that says, one second. Also need to add something that says maximum, how do you call that now? Maximum coordinates. We could call that max x, max y, just for semantic purposes. Again, you don't want to get bogged in, overthinking the requirements just now. You just want to capture them anyhow, no matter how inarticulate, and then come back and deal with them. The rest of the input is information pertaining to the rovers that have been deployed. Each rover has 2 lines of input. So if we take out the 5, 5, which we just dealt with, and in this case, in this example, was 5, 5. Did I just put a comma? Did I just see that there's no comma in the input? So it's just 5 space 5. So if we do this, we have 5 space 5. Okay. All right, I think, okay, so we're going to have to come back and modify a lot of those coordinates we've been doing, the xy's, because if you look at this, 1, 2n, 3, 3e, but we'll come back to that. This line here says the rest of the input is information pertaining to the rovers that have been deployed. So if you take out 5, 5, you have this line, 1, 2n. The rest of the input is information pertaining to rovers that have been deployed. This description does not say that 2 rovers have been deployed, or 3 rovers have been deployed, or 1 rover has been deployed. It just says the rest of the input information pertaining to rovers that have been deployed, and each rover has 2 lines of input. Meanwhile, we have 4 lines of input here after taking out 5, 5. That implies that we have 2 instructions, 2 rovers here, because there are 2 lines of input per rover. So each rover has 2 lines of input. So if we take the first rover, 1, 2n, and lm, 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 lmm, and then the other one, 3, 3e, mm, whatever that is, each. So the first line gives the rover's position, and the second is a series of instructions telling the rover how to explore the plateau. I think this is pretty straightforward. So if we look at it now,
it's
what this
11
means
o'clock.
is that in the command object, did you call it a command or a message? In the command message, the first line is map plateau size. The first line is a plateau size, and that is 5, 5. The second line is, now the second, I wouldn't call it the second line, I would say the second component of that message object is an array, just to use an array, loosely in this case, is an array of rover instruction objects. If I can just quickly create, if I can just, just for semantic purposes, where rover instruction itself contains 2 lines, because what we have here is, this, in this example, is just 2 rovers. The next example we get, for all intents and purposes, could be 3 rovers or 5 rovers or 10 rovers. So we have to factor that. So that's something that's been communicated here. 1, 2n, lm, lm, lm. So there we have rover instruction. We have the rover position, first line, and rover, what do we call that now? Rover movement or rover command. Now we can use it. Now we can use a command, because it's a specific command to the rover. Rover command, where each rover instruction object contains a rover position and a rover command on the second line. All right, we spent a lot of time sharpening the axe, interpreting the instructions, but I don't mind spending 90% of my time understanding what to do, and then 10% of the time doing what I can with the right understanding, than to just jump into a pool without knowing how deep it is. All right, so that's that. The position is made up of 2 integers and a letter separated by spaces. That's pretty clear. 1, 2, n. Over here is 1 letter, 2 letter, 1 integer, 2 integer, and n letter, corresponding to the x and y coordinates and the rover's orientation. Each rover will finish sequentially, which means the second rover will start to move on to the first one and finish moving. The output for each rover should be its final coordinates and heading. All right, and I guess that's this and that. Okay. Now, from this, what are the lessons we have learned? As you can see, we've extracted quite a number of objects. We have a mission object, which I guess became our message object. So the mission object is kind of redundant right now. That's what we call the message. We have the rover object that contains a position and a location. And then we have the plateau object, which contains a grid of positions. Okay. We also have the inputs, which contains which just specifies the format of the message. So I can, or we can, this is collaborative, we can deduce that expected behaviors from this system are that the rover should spin left. That's one behavior. Rover should spin right. Rover should move forward. Okay. So many typos tonight. What's up? All right. Rover should spin left, spin right, and move forward. These are at least 3 expected behaviors from this system. Can you think of any other? For now, we have enough to start. The thing with the thing with software development is, especially if you are familiar with agile mindset and way of work, is that you don't want to wait for 100% clarity before you move forward. So we have enough to work with. We have these 3 behaviors that I've just listed out: spin left, spin right, move forward, are actually our first unit tests. So if we go to our project here and we add a new project and back to .NET Core tests, which one should we use? Just for the breadth of opportunities available, let's use XUnit, okay? Because XUnit is the base of NUnit and JUnit, PyUnit and all the others. So let's go. Project name would be Mars Rover tests. Okay. And that will be in the same folder. Create a project directory and create. Okay. And so we have our test project called titled our test class, our first test class, test project and test class, titled unit test 1. I just call that. So there's something that I did here without explaining. So with TDD, the word should is a word that has a significant meaning because it helps to define it kind of helps to identify the units of behavior that are about to be implemented or that are about to be defined as tests. So watch what I'm going to do here. I'm going to rename this class to Rover should. Okay? All right. The moment I do that, I get that here, and I need to refactor this to Rover should. Luckily, I don't have any references to it just yet, so everything should be fine. And then this one called test 1. Can I also refactor it to give me a test? Just give me something. So we had here 3 behaviors: spin left, spin right, move forward. Let's do the first one. Let's just call this spin left. Okay, Rover should. So you see what I did here? My sentence, my expected behavior sentence. So if I come here and I say, come on, behaviors. Okay, so, oops. Expected behaviors. Rover should spin left. You see that Rover should becomes the name of my test class. Okay, the first 2 letters. So your object. So when we get to, if we want to build tests for the plateau object, it will then be plateau should something something. Message should something something. And so on and so forth. You get the drift. So that's spin left. Okay, so the easiest thing to do, I'm going to just for a template so that I don't forget it, and by the time I start to do copy and paste with unit tests, I don't leave it out. I'm going to create the arrange, act, assert paradigm here. Now, this is a popular pattern for unit test development that helps you to remember to always do the required things. So the arrange comment is where you put all your setup and infrastructure. Well, infrastructure is a big word, but setup tasks that are required to, do the current test. Your act is where you actually carry out the action, and then your assertion is the testing instruction, which we should return if true or false, or should return something that verifies that the test passed or it failed. So, similar to the assert, arrange, act, assert paradigm in TDD, there's also a paradigm, a three-word paradigm in TDD called the red-green refactor paradigm. So the first thing, red stands for failing test, green stands for passing test, and refactor stands for continuous improvement. So the first thing you want to do is to make sure that your test passes. There's quite a lot of intuitive benefits to this, but it sounds counterintuitive that why are you trying to write a test that should fail? But it is what it is. Write the test and make sure that it fails. That does a lot of things. It proves that your setup is working. But we'll come back to that. I don't want to talk too much, but I want to make sure that you know what I'm doing. So the first thing I'm going to do is I'm just going to assert true, assert that something is true, and then I'm deliberately going to put a false in there, just to prove a point. Okay, and then somewhere in here where we have our okay. Oops, cancel, save, and save. Why is this guy not saving? Okay, that's good. All right, so time to run the very first test. Rover should run all, and we will see the results in this panel over here. All right. Okay, we're still building. If you look here, if you look up here, you see that we're still building. Oh, there's a download going on. I have something going on. Okay, so build was successful. Mars Rover tests. Where's my results? Okay, the tests are running. Tests are still running. This is not yet a red. So you see that I have the stop sign, the stop button, the cancel button has gone off. So that means my test has completed. And you see that the first item here is red. And all of the children are red. Actually, I have only one test. So no matter how many layers of hierarchy you have, I have only one method that I've implemented, which is the SpinLeft method, test method rather. And you can see here that it is failing. Okay, if you go to if you were to deselect all of these and then you go to failed tests, you would see that assert true, failure, expected true, but the value was false. Okay, so that's good enough for a test to fail. The next thing we need to do is to make this test pass. And then the TDD way of making test pass is not that you then go to your method or to your proper, class structure and start to write a lot of long code. TDD says write just enough code to make your failing test pass. So somewhere in here, in fact, I'm thinking that we should rename program to Rover, and then later on, but let's just leave program. Let's leave program, and let's create a new class called Rover. Okay, add new file, empty class, and I'll call it Rover. Alrighty, so the first thing I want to do is that I want to public class Rover, okay, and I have a constructor, a default constructor. The first thing I want to do is that I want to make this test pass. What's the minimum set of tests I need to do to make this test pass? In order for a rover to spin left, if we go back to our problem description, it says here, in order to control a rover, NASA sends a blah, blah, blah. LR makes the rover spin 90 degrees left or right, respectively. Okay. And if you think about rotation and spinning, if an object is facing a certain direction and you were to spin 90 degrees in another direction, you are not moving. You are essentially changing the direction, okay? So what it means is that if you're going north, if you're currently facing north and you rotate and you spin left, you would be facing east. If you're currently facing north and you rotate left, you'll be facing west. You would be facing west. Okay. So spin left essentially just modifies the orientation or direction property. How did we capture that in our program comments? We had said earlier that so where you have the XYZ, spin left modifies the Z. And in here we have, in there we have, for this 1, 2, N, spin left modifies only the N. It doesn't effectively make any changes to the X or Y coordinates because it doesn't move from where it is. So that itself implies that we should have defined certain properties. Just for the ease of doing this is not the proper thing to do. The proper thing to do is to create properties with getters and setters, but just for the ease of doing this, let's create public properties that represent those three characters. So public int x, okay, let's just define that, okay, public int y and public int direction. If I can add some comments here, I would say x coordinates of the current rover position. And if I can add a comment here, I could actually just copy this. Keyboard is your best friend as a programmer. Y coordinates of the current rover position. And then this would be cardinal. They use the word cardinal direction if I haven't forgotten, of the current rover position. So if we go back there, there's something that says something about cardinal compass points, representing one of the 4 cardinal compass points. Blah, 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 left or right, without moving from its current spot. I maintain the same heading. Let's call it heading. Perfect. Let's just leave it as direction. Heading sounds a bit technical for those of you that are geography majors. All right, so the constructor typically is where you initialize variables. So I would say that the first thing the constructor should take is the constructor. What are you constructing? You are constructing a rover object. The rover object takes, where's my program? Scroll up. The rover object takes XYZ, which in this case is 1 to N. So I can take this as a string. I can say that the input, that's not the right class. I can say that the input in here is string. What do you call that now? Was that the rover command? Rover string, let's just call it location, let's just call it location. All right, public rover string location. So what's going to happen here is that we're going to have to split that thing, that location parameter by, because it's delimited with spaces. So your usual arrays are delimited by commas, but this one is delimited with spaces. So we need to say that x equals location dot split. Perfecto, thank you. Split, and then we have a space there, and then the index is 0. So the x is always the first entry in that message. Cannot implicitly convert type string. Oh, so there's a try parse function, and if I'm correct, this usage is wrong. I'm going to have to say int32.try parse, and then I'll have to do something like this. If I remember my syntax correctly, I do int 32. What am I writing it again? Control C, Control V. int32.try parse split number 1, the second parameter, and store y in there. And then, do we need to copy? So the third parameter in here, in this 1 to n string, is the n. N is not an int, so we don't need the whole try parse business. So let's just say that direction equals location that splits to, and we should be good. Are we? No, we're not. Cannot implicitly convert type string to int. Oh, did I declare direction as an int? Ooh. All right, so this gives us the basic rover objects. Okay, so technically speaking, we haven't gotten to where we start to implement this. So if we try to implement the SpinLeft method now so that this guy can pass, some people like to use the, what you call it now, public void SpinLeft. Okay, public void SpinLeft. If you try to implement the SpinLeft, some people like to use standard, some people like to throw exceptions, standard.NET exceptions, or if they create their own custom exceptions, they like to throw them. There's a popular not implemented exception, which we can just do now. So in order to make SpinLeft pass, ideally what you want to do is that as much as possible, you want to make your unit method names, unit test method names, match with your actual names. So in the terminology, in the self-documenting terminology of unit tests, what this does is that if you look at the hierarchy, in the Mars Rover test namespace, the rover class the rover object should spin left. That's what this test is all about. So in the rover object, there should be a spin left method. And this was wrong. I should have a camel. I should have that's Pascal case. So public void spin left, and then we have, public void spin left, Okay, so we want to pass. The first thing I will do is I will just say throw new not implemented exception. Okay, I'm just going to do that, and then instead of assert true and false here, I'm going to try to actually run this method, okay, all the way from here. So I'm going to say public void spin left in my test. I'm going to say arrange. I'm going to define a rover object. So if I define, public void, public class. Why is my rover not available? Why is rover not available? Generic class? No. Excuse me. Okay, so I just need to be sure that this guy is a public class. It is. Visibility is open. Public rover, public void. Okay, rover equals there we are. New rover. Okay. Are you missing honors? Oh, of course, of course. Okay, so I haven't created what you call a reference. So I need to add a reference to, no, I don't want to do that. So I need to add a reference to this, to the main class. Okay, but the reference is, where are those references then again? It's been a while. Add. Okay, so if I right click, all right, there we are. Edit references, Mars Rover. Okay. All right. So so it should now understand. All right. Thank you. There's no argument given that corresponds to the required formal parameters location of rover. So let's just, just to make this test pass. That's 1 to n, 1 space 2 space n. And that's a string. Okay, so that's our range. Under act, we want to use this object. So we actually want to say rover dot, can you see it? SpinLeft. Okay. Okay, SpinLeft. And then now we're not asserting true. We don't need to assert true. Okay, so we could take a variety of approaches. We could say assert that the following condition is true. And then we could say when you spin left, if so the literal comes first, and that is, so when you're facing north, because our parameter has 1 to n is north, and you spin left, you would be facing west. So if we say W, so I'm thinking in terms of the syntax of, I'll come back to that. I'm thinking in terms of the syntax of the assert.equal method. But because we want to use true here, we could just say rover.direction equals west. And if we run this, we should have a passing test. Test still fails. Why did it fail? So if we go here to the failed test section, system.not implemented exception. Ooh, why is that? If we go back to Rover, that's because we actually have not put in code here that does the actual changing of the direction attribute. What we've done is to throw an exception. And exactly as you can see here, the same exception was thrown. This is the only place where we've instantiated, not implemented today. So that's actual feedback. Even though the test is failing, it's feedback that it is failing right, if there's such a phrase, if there's such a term. So what we then need to do is to build out this method. So what's the logic? Shall we use a switch or an if-else? Just before we do that, I said I was going to explain two approaches to the assert. So we could have done this, which we did, assert.true this, or we could have done assert.equal, just to give you a breadth of options. Assert.equal, and this is where the W that I was typing earlier comes to pass. The literal that you want to compare, comes first, and then you have rover.direction. So essentially, this may be an overkill for a string comparison, because technically speaking, the W and the rover.direction are not equal in terms of equality of objects in object-oriented design and programming. But I mean, just for the purposes of this test, is okay. So we can use any of them. If we do this and we run the test, it should still pass. Ooh, this time it actually will. It did not pass. Assert.equal is W, but it is still N because we didn't do anything to it, so we didn't make any changes. So you see what happened because I had commented this out. If I take this back so that we have the exact state of the program that we had it, we can do that. So there you go, and you have not implemented exception. So let's quickly deal with this, and we might call it a wrap just after one or two or three methods. So assert.equal west rover.direction. All right, throw new implemented, not implemented exception. So what we want to do here is we want to put in some conditional logic that determines where we are currently facing and then changes it to where we should be facing after rotating in the direction of left. So if we say switch, okay, switch direction, case, what's the first case? N, which is the situation right now. Case N. Set direction to be equal to, when we're facing north and we spin left, we would be facing west. If you're in Africa, you're facing north, and you spin left, you would be facing South America. So that's W. And then we have our break to complete that. So technically speaking, this is the minimum amount of code that will be required to make that test pass. So let's go. Run. Even though we haven't implemented the logic for the rest of the function that will test for west, east, and south. But you can see that, yay, we got our first green test, our first passing test. Okay. And you see how you see the thinking that goes into test-driven development now. Now, if we go back to this place, and I change this 1 2 n to 1 2 w, and I run this thing right now without making any code changes. Obviously, if you're facing west and you spin left, you won't be facing left, so we don't expect this to pass, right? Did it pass? It did. Ooh. Why did it pass? So that shouldn't pass. I said that equal west over the direction. Okay, you know what? In order to save time, let's just go ahead and fill out the other. Or if you're so we could add a breakpoint just before the break. Okay. Then if we run it, you know what? Let's not waste time on that. So let's do a 1 2 n. I said that equal w over the direction, and then let's deal with this. Case n, I think we spent over an hour. I'm not sure when we started. 2, 3, 4. And then for the default, I'm going to throw new argument exception. Okay, so n here, okay, n east, south, and west. So when you're facing north and you spin left, you would be facing west. When you're facing east, which is your right side, and you spin left, you would be facing north. So this should be n. When you're facing south and you spin left, you will be facing your right side, which is east. You're facing right, which is east. When you're facing west and you spin left, you will be facing south. NWES. So that's that. So of course, when you throw an exception, the break is going to be unreachable. So that's that. Now, something tells me that we need to pay attention to this. Let me just clean this. And rebuild. Okay, so right now we have 1 2 n. So I could just write something out to the screen. Oh, sorry, that's rover.direction. There's a way of debugging. All right. Where's my immediate window? Okay, so if I make this 1, 2 south, why? Why did it fail? Because when you're facing, it was expecting west, but when you're facing south and you spin left, you would be facing east. So that's working properly now. When you're facing west and you spin left, you would be facing south, not west. So if we run it again, you'll be facing south. If you are east and you went that way. So I think we're fine with this. So spin left is pretty much done. So if I change this back to N, you see that we have a working solution, no matter how small, okay? The next thing to do would then be to, so we have, remember that we had 3 units of functionality that we thought were important. Spin left, we've just done that. Spin right and move forward. Sometimes you will discover that writing the test harness for your first few methods is usually takes the longest, because you have a lot of thinking to do. But then, for the similar ones that follow, you should be able to move faster. So if we were to quickly move on, we could do spin right here. And then under arrange, instead of spin left, I would say spin right. Knowing fully well that I haven't written the function, but that's not a problem. We'll just tell Visual Studio to generate a stub for it. Oh, and you see, now I'm carrying over a lot of things. The asserts thing and the console thing. So, that's why it's good to clean up your boilerplate code before you start copying it all over the place. So, spin right obviously does not exist, so I'm going to tell Visual Studio to create it. Thank you. Create a method called spin right. And then if I go to my rover class, I see a method called spin right under spin left, with its own definition. So if I then call this gentleman, so if you're north and you spin right, you won't be facing west, you will be facing east. Okay, and so if I run this now, we should have 1 passing test and 1 failing test, and the failing test should have an exception of not implemented. So if you look closely at rover should, you saw that earlier on we had the entire hierarchy of tests was red. Now we have a half and half red green, which partial green, partial red. And then the second one is the one that is wrong. Successful tests, over there you have the spin left is successful, but spin right was unsuccessful. And why was it unsuccessful? Not implemented exception. So I'm just going to do this. I'm just going to copy this gentleman all the way here and dump here. Okay, so Now, we need to be careful with this logic. So when you're going north, if you spin right, you would be going east. When you're going east, if you spin right, you would be going, don't touch that, you would be going south. When you're going south, if you spin right, you would be going, you're going south. If you spin right, you'll be going west. And when you're going west, if you spin right, you'll be going north. Okay, so that satisfies our conditions. And if we run the test again, I just told you that, I just mentioned that in unit testing generally, though, your first few tests require the greatest amount of thinking. You can see what we did, the amount of work we did to get the first test passing successfully and to cover all cases was significantly much more than what we did for the second test. All right, so that's that. The third one, rover should move forward. Now, let's think carefully about rover moving forward. If we do this, Control C, public void. So if I, oops, that's anti-TDD. What I just did was anti-TDD. I wrote the code first without thinking about the, so what I should be doing is I should be writing the unit test for move forward. Okay, so now I'll change this to move forward. But you know what? I'm thinking that actually the keyword move is slightly misleading. Move is actually a combination of spin and step forward. Okay, spin left as the case may be, or spin right as the case may be, and then step forward. So it could be spin left, step forward, or spin right, step forward. Together make a movement. So if we can, if you permit me, I will rather use terminology like this, step forward. And this happens all the time where you're doing test-driven development, that you, as you understand more, as you glean more and more insights into your solution or your application, you're going to, refactor, which is continuous improvement. You're going to keep on doing more and more of that, as the time goes on, So over here, when you step forward, for spinning left and right, the action of spinning left or right was modifying the direction parameter. The action of stepping forward, depending on where you are facing, will modify the X attribute in some cases and the Y attribute in some cases. So we need some logic to determine where you are facing and what is appropriate to change. Okay. All right. So we can still instantiate the rover. The method name will then become step forward, and we'll tell Visual Studio, our best friend. If I wanted to cause trouble, I would just say something like Visual Studio is the best IDE in the world, and all the programmers in the world will come for my neck, like Thanos' neck, So step forward. So you see your step forward there. Thank you. Okay. If you don't mind, I like some visual, they call it syntactic sugar, visual, whatever. I just like to align things properly. So step forward, technically speaking, is not throwing any it's not showing us any design time error here, because the method does exist and we've put in a throw new implemented. But we know what it would do if we run it. We're going to have 3 methods now, and the third one will fail with a not implemented exception message. But what we want to do is that's that. So if we go to step forward, you see that not implemented. Before we fix why it's not implemented, when you step forward, let's say you are at position 1, 2, and you were facing north. If you stepped forward, you should be at position 1, 3, N, because you're facing north. You're going northwards from 1, 2. 1 represents the X, 2 represents the Y. And when you're facing northwards, you'll be modifying the Y-axis. So what we should be checking for on the equal method should be, instead of a string, this will be 3, and this will be, instead of direction, Y. This should do it. Okay, it will still fail when we run it because it's still not implemented in here. Okay, but it's good to run it to establish that it's failing because we want it to fail. Now we have the presence of mind to go into the method and build out the logic that will fix it. Again, we may not build the logic for all cases of direction. Okay, switch direction. In fact, why am I writing a new switch? Why am I writing a new switch when I have a switch here for the same values? Okay. Okay, switch direction. Case N. But what we're modifying is not direction property. When you are facing north and you switch and you take a step forward, your Y, what do you call that? You know, the Y components of your position would increase by 1, which we could, for syntactic sugar, rename to refactor to plus equal to 1, or even, what do you call that thing now? Yeah, back in the day. Let me just use something that I'm sure everybody understands. Y plus equal to 1. And then over here, when you're facing east, east is towards China. When you're facing east, if you take a step forward, you would increase your X by 1. When you're facing south, facing South Africa, Madagascar, you would decrement your Y. And when you're facing west, you're facing the Americas, you would decrement your X. Okay. Oh, have I lost something in the process of copying? Oh, I think I lost someone here. Okay. All right. And if the wrong value is supplied, just throw an argument exception. This should fix our bug. Let's try. Let's find out. Step forward. Oh, we're fine. So when it's N, it's 3. When 2 is on the y-axis, it's 3. If we change 2 to 0, then this should be, and you're still facing north, then this should be 1. Right? Still passing. Yay. If we change this back to 2, no, it will always be, or rather, good. If we change this, instead of north, we change it to south, then we would expect for south, what do? You decrement the y. We would expect this to be 1. Okay? Let's run it. And it should be green. It's green. Okay? And just to be sure that it's not a fluke, if we put a 3 there, run all, it should fail. Okay, so was expecting 1 and it was expecting 3 and it got a 1. Oh, actual 1 should be the other way around. All right. So 3, 1. This was 3 and this was north. Okay. So we have our solution right there. Public void, spin left, spin right, and step forward. Something feels missing. So what we've done is we've done the basic building blocks of movement. So spin left and step forward are a movement. Spin right and step forward are another movement. So let's go back to our problem statement and see if there's anything we missed out. So technically speaking, this is how the instruction comes out as appears on this line, the line where the cursor is. LM, 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 LMM. That means left move, left move, left move, left move, move. So if I were to implement that, or if I were to build a test from that, I would say rover should go to, and I would say 1, 3n. Okay, so in my rover should, I will create one more test method and call it should go to 1, 3n. Or arrive at. So if we start from 1 to n, then I could say 1, 3, what was it now? 1, 3n is equal to rover.x, I hope you're following, plus space, actually concatenate, not plus, concatenate space, concatenate rover.y, concatenate another space, concatenate rover.direction. And this method should be go to location. Or move to location. or just move. Okay, public void move, and then my comments here, rover should move. Okay, so rover should move. Let's fix that quickly. Okay, and in that method, of course, if we run it now, we're going to have a failing test. And it will be because it's not implemented. Okay, as you can see, move failed for not implemented, which is what we have here. So let's build out this functionality.
It's 12 o'clock.
So what does move take? Move takes this string. I wonder if I can copy it because this thing has been, I'll just type it out. LM, 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 that's 3 LMs and then LMM. Okay, so let's do this. Let's say string rover instruction. If I remember correctly, that was what we defined here as rover instruction. Perfect. Yes. Or rover command, actually. So throw new not implemented exception. So essentially, this is really not dependent. We're going to be calling spin left, spin right, step forward, whatever, depending on what we're doing. But what we need to do here is that we need to break down this string into individual instructions. So we can do, and they are single letter instructions. So we can just say, array of instructions. Okay. Let's say we have a car array and we call it instructions and we equate it to rover command dot to. Thank you, we have it. Okay, and if we take that this example is 3 LMs LMM. Okay, so our values are in that place, so we need to loop through array for each letter call spin left, spin right, or step forward as appropriate. Okay, so how do we loop? Let's do the for. Again, Visual Studio is the best IDE in the world. Some people will break my neck. So for int I equals 0, I less than instructions.length. Okay, we never want to get to the maximum value, so we're not using a less than or equal to. So while you're looping through this array of car, please compare switch again. Switch no, excuse me, instructions I, our variable is I, okay, switch instructions, okay, in the default case, oh, we're dealing with cars, so case L, let's say is left, you would call SpinLeft. And then you would break. Case M, you would call, ooh, that would be case right. I'll come back and fix it in a moment. And then you would break. Case M now, you would call step forward, and then you would break. So let's change this to R. And if anything is supplied that doesn't match these conditions, please throw an argument exception. Okay, so I'm going to test it with this string. And let me quickly get what the other string is. The other string is mmr mmr mrrm. So it's mmr twice, mrrm, mmr mmr mrrm. Did I get it? mmr mmr mrrm. mmr, gotcha. Okay, so those will be my test arguments. So if I do this, if I copy this and use it in my move, so as you can see, my move command needs to take a parameter, which is why this has been read. There's no argument given that corresponds to the required formal parameter. Oops, no, that's not a variable. And then if we do this, our instruction says if we're at 1 to n and if our rover is at 1 to n and we're given this instruction, we shall arrive at 1, 3, n. So this test expresses that our rover is at 1 to n, starting point. We move according to these instructions and we should arrive at 1, 3, n. And 1, 3, n should be equal to rover x plus rover y plus rover direction. If that is so, let's test the middle of what we just wrote. We should now have 1, 2, 3, 4, 5 methods. 4 methods. Ah, that feels like magic. You know, so we have move, spin left, spin right, and step forward. Okay, the output for each rover should be its final coordinates and heading. I don't know what to say. The only thing to do now is to verify that this also passes. So if I pass this, actually this is for another rover, so 33E, and then that instruction will take us to 51E. So instead of 1 to n, we have to have 33E, and then instead of 1, 3, n, we have to have 51E. Just to be sure that I haven't written rubbish. 33E and that instruction, checking for updates, you can close. Oh, so updated everything except the ID itself. We can come back to that. All right, so 33E and MMR blah blah blah. 33E and blah blah blah, and then the output should be 51E. Output should be 51E. So let me just deliberately, because I want it to fail, okay? And then I'll put the right property and see it pass. Thank you. So it was expecting 51E, but it got 11S because we gave it another instruction. Okay, so if we do put it at the proper instruction, yay! Congratulations, we have a set of tests that pass and the minimum required code to implement the requirements that were given. So if anyone who's watching this video, if you ever wondered how do you build test-driven development applications, TDD applications, you don't have a right to say you don't know how to do it anymore because you have seen how it is done. Thank you very much. We'll be closing right about now.